In the last few videos, we've been tackling some particle motion problems, and now we are on page 529 in the notebook. And so we will start working on a different problem. So this time we've got that the velocity of a particle that's moving along the x-axis again is given by the function v of t is equal to 0.5 times e to the t times t minus q quantity cubed. Holy cow. But this is a calculator active question. So in the last problem, it was a pretty easy function to find an antiderivative of. I couldn't imagine trying to find an antiderivative of this. It would take me all day if it's even possible. But since this is a calculator active question, I can have the calculator tackle this problem for me. But if the position of the particle at time t equals 1.5 is 2.551, what is the position when t is equal to 3.5? All right. So once again, we're going to solve this in the same way we solved the last problem. We're going to set it up in the same way using the fundamental theorem of calculus. So take a second, pause this video, and see if you can express that here. So we've got the definite integral. The two times we're interested in are 1.5 and 3.5. And I'll put in v of t here, 0.5 times e to the t times t minus 2 quantity cubed. Let me warm up this calculator because I can see this coming our way. All right. New actions. Clear my screen. Wait. All right. And that is equal to, I'm going to call it x instead of p. I think that's a much more common variable to talk about the position along the x-axis. All right, and so now we're going to calculate these three things. The time at 1.5, position at 1.5 is 2.551. X of 3.5 is what we're trying to calculate. And so what's different about this problem is that rather than trying to find an antiderivative, I'm going to use my calculator to calculate this area for us. So menu, calculus, numerical integral. And so they stick all of that in there. Let's see, how can I set this up so that you get the maximum resolution of that? All right, so 1.5 to 2.5 of 0.5 e to the t times t minus 2 raised to the power of, okay, so that's the caret button, raised to the power of 3. All right, and then we need to stick in the dt here. All right, so we calculate that, and that gives us negative 293.011. Let me also include the dt right there. I forgot to do that. So that's negative 293.011 is equal to x of 3.5 minus 2.551. So all I need to do is add 2.551 to that, and I get negative x of 3.5 is equal to negative 290.46. And once again, we want to know what is the total distance that the object travels on the interval from t equals 1 to t equals 5. All right, and so this time, maybe I'm going to go to the graph screen. All right, and so I need to clear off the graph that I already had here. Menu, actions, delete all. Yes. All right, so I'm going to press tab and I will put in 0.5 e to the, now remember when you're putting a graph in, even though this function is given in terms of t, you'll always need to enter it into the inspire in terms of x, because a graph is on the xy plane. E to the x times x minus 2, close, caret 3. All right, and so remember, we're interested in the range of this. Well, here they're talking about the distance from 1 to 5. So looking at this, I can see that we've got a problem that this is going to be negative between 1 and 2, and then positive for the rest of it. All right, so there are two ways I can handle this. The first way is I could just calculate these two integrals separately, from 1 to 2 and from 2 to 5, and then add them together. But what I might do instead is I will come back here and I will put in the absolute value of this. All right, and you see how now everything is positive. It just took the negative parts of the graph and flipped them up to the top of the x-coordinate. And so now I can calculate this definite integral. All right, and I want to have it start at 1, 2, 3, 4, 1, 2, 3, 4, 5. All right, and so that gives me an area of 91.3. Okay, again, I could have calculated that on this page, but I would have wanted to be careful to throw absolute value symbols around this thing just to be sure, because they were talking about the total distance. Okay, so that gives you an idea of how we can solve these problems when we've got a more complicated function, but we're allowed to use the graphing calculator in order to solve it for us.